Um, there was a question about the last question. I will send you the question log. Whenever you're ready. You're on.
That's me.
Oh, really?
Yeah.
Oh, you're logged in the other room there. Okay. Okay. So we have two people that are logged.
My name is
Anyone actually on listening at the moment?
Lessons learned from our on-orbit anomaly research effort.
Oh.
Hello?
So our agenda, our
Justin,
plan
are
for
you there? They're in.
do a brief introduction about the on-orbit anomaly research effort
Tell you
here
what.
at the facility.
I'll
Talk about the goals of the
response to
presentation, and then go over some representative anomalies that we've had or have seen over the past couple of years. The on-orbit anomaly research effort is an effort here at the NASA IV&V facility in Fairmont. And we have a couple of objectives. Our primary objective is to analyze anomalies that have happened on NASA spacecraft and provide recommendations to improve IV&V processes based off of investigations on those anomalies. Our team consists of 4 people, myself.
Apparently, what she did was capture the question.
Koorosh, Mirfakhraie, who's part of our team as well. And
that doesn't make much sense.
In respect to the investigations, they can take anywhere from a week to several months, depending on the scope of the investigation. And what we do is we look at the anomaly, the root cause of the anomaly, and if applicable, the IV&V activities that we performed on that spacecraft, and try to develop lessons learned or recommendations to help the NASA IV&V facilities here in the future. Again, the facility here is more focused toward flight software and software type anomalies, so that's typically what we focus on. A second thing that we've been doing is to brief analysts on new and emerging technologies that have an effect on mission flight software and have been shown to relate to some anomalies we've had. Actually, for the second objective, the anomalies we look at are often a driver for developing resources on new technologies because anomalies happen because of them. So one of the things that we try to do is to keep analysts informed on the intricacies of some of these newer technologies and provide assets for them that they can use to improve the analysis of the facility. So what are we going to talk about today? Well, one of the things, obviously, we're going to talk about some of the findings and lessons learned we've seen in our research. And we've chosen 5 anomalies that are representative or have themes related to some of the issues that we've seen across multiple projects. Keeping in mind, there's 30 minutes roughly allocated for this presentation. So the anomalies that we picked were picked to be more self-contained and understandable within that time period, and also just to ones that we thought that could provoke thought and provide value to people more focused on software IV&V research. We do have a couple of caveats. One of which is that in exchange for our anomaly sources, we have agreed not to communicate the specific name of the projects that we've done our research on outside of the facility. So the ones we look at today have been anonymized mostly in a lot of the data specific to the projects has been sanitized out of it. And we don't believe that that really affects the results very much. And also in a couple cases, some of the anomaly descriptions have been simplified slightly to fit within this format. If anything required some in-depth explanation of highly complex control circuits or sensors or something like that, we may have simplified the exact component that caused the issue for the sake of not having to delve into the intricacies of that in the future anomalies. We have 5 themes. Ooh, that's kind of off. Oh well. But the main things we're going to talk about in each anomaly, we're going to have the anomaly description, which is basically what is the bad thing that happened here. So if the spacecraft went into safe hold mode or crashed into somebody's car or whatever, what's the bad thing that happened? So that's the anomaly description. And the background information, cause of anomalies, self-explanatory. It's what you need to know to understand what happened. After that, we're gonna talk about briefly the project solution to it. A lot of times it doesn't have as much relevance to us from an IV&V perspective, but that's a question that we get a lot. So we just decided to answer it up front what the project solution was, and then we're going to talk about some of our observations in respect to the anomalies, and also some takeaways from an IV&V perspective, maybe, or some thought-provoking some things. And obviously, in some cases, we don't necessarily have the solutions to implement these things, but we think one of the big things that we'll deal with is identifying the problems. And so if we have evidence that says, hey, this specific type of thing tends to occur on multiple missions, then we really want people to be able to know that, whether or not we have let's add this IV&V process to be able to fix it. So that is that. And so we're just going to jump into our first anomaly. And the anomaly description on this end. And there's a lot of text in these, so I know it's a little early in the morning. We're going to have to use our imaginations a little bit. I'll try my best to be clear in the explanations. I use my hands some, but I can't because of online. So I'm going to try my best here, and you guys are just going to have to stick with me. Maybe take a sip of whatever caffeinated beverage you have, and we'll try to get through these. So basically what happened in this case is we have a measurement device on a science instrument, and it's disabled at the start of a blackout period, just like it says. And there's a command that after a blackout period re-enables the instrument. And in this specific case, that re-enable command failed and led to a loss of science. So on this particular spacecraft, imagine we have 2 identical instruments, and these instruments have 2 properties. The first property is whether or not it is the primary device, and the second property is whether it's on or off. So we have these 2 instruments, and they kind of alternate during the process of the mission. So one will be primary for a couple months, and then it'll switch to the other to be primary for a couple months to give each one of them a rest. And obviously it can be each one of those instruments can be on and off. Because of some environmental constraints to the mission, there are certain times where these instruments have to turn, and just for safety reasons, and then they can be enabled out of there without limitation. So in the times when blackout period is needed, basically what happens is the ground runs a script which contains a series of commands that disables the primary version of the instrument, and then it runs a script, which is a package of commands to re-enable the primary. In this particular instance, there was a flaw in the ground command script for the enable and disable, in that the command was hardwired for device 1 only. So if you have 1 and 2, it was hardwired for 1. So whenever the command would go up, it would just say disable 1, re-enable 1, regardless of whether it was active or inactive or whatever. One of the things that kind of helped in this case is that we did have flight software. Did have fault protection in flight software. So we have a blackout period coming up, and the ground sends up a command that says disable the active device. Well, flight software fault protection says it has a rule in this case that says if I get a disable command, regardless of whether it's for device 1 or 2, we're going to disable both of them because this is a safety issue and we don't want something to go bad. So even though this command was hard coded for device 1, fault protection in this case did the right thing and actually maybe helped save part of the instrument, and it disabled both of them. So even though it was labeled for device 1, device 2 at this time is active, and it disabled both of them. But afterward, whenever the re-enable command comes back up, there's another fault management or fault protection feature that says we will not allow a device to be turned on if it is not the primary device. So in this case, the command came up to say, we want to turn on device 1. Device 1 wasn't the primary device at the time. And so fault protection correctly said, no, that's not the primary device. We're not going to turn it on. So in effect, they were stuck. They couldn't get the correct device on. So they had to go in and do some manual commanding to be able to re-enable device, the second device, which they did. So the cause of the anomaly was device 2 was active, and because of the command sequences and how everything was labeled, the correct device was disabled, but whenever the re-enable command came, it was rejected. So the project solution was to manual command device 2 to be re-enabled, and our observation for this was basically this anomaly was due to a command script used in ground software. It was not a flight software fault per se. Flight software did in fact prevent maybe a more serious issue from occurring, and it could have been damaged if it wasn't in the way. One of the reasons that the category for this is kind of pseudo-software command scripts, which is a little bit abstract, but one of the main reasons that we put this in is we've seen multiple anomalies that originated from ground system commands, and so this is one particular case of that we thought that we could share in a short amount of time. But the other thing is fault software couldn't really do anything to stop it at the end, and potentially if ground software was in a better position, we could have caught that. Our IV&V lessons for this kind of go back to the ground software thing, is that in effect, in certain circumstances, especially when it comes to scripts or packages of command to perform operations, ground software is kind of an extension of flight software. And one of the things that we think is important is that if ground analysis is in scope, that the kind of commands that are used to perform specific maneuvers, maybe not as much stored commands, but scripts that have a series of commands to perform specific operations should be looked at and evaluated from an IV&V perspective. And this may be, and we recognize that this may be somewhat difficult thing because IV&V isn't around for software operation, and some of these kind of scripts might be some of the last things that we would see before we go out there. But according to the anomalies we've looked at, there is some value in the ground commands coming through. So if ground analysis is in scope for IV&V, it's definitely important to look at that. It's the source of several anomalies, and it just is a really good idea. The second thing is, if ground is out of scope for an IV&V project, what do you do? Well, the fact is that there's probably going to be certain commands that are run whether or not the stuff's in scope. So one of the things that we've seen in some of the software we've looked at is typically like if you're looking at the actual code, there's a directory for each module flight software that's called utility, and usually those utility functions are things that can be invoked remotely by the ground for whatever and pass a certain value, and the utility functions for a module do a certain thing. And so from an interface perspective, if there are utility functions that are not exclusive to flight software, making those calls that can be invoked from the ground, particularly, those could definitely be a target for analysis in respect to evaluating scenarios for when those kind of functions would be used and what would be the purpose of that function to get to alleviate a certain situation, or how would those utility functions be used. So I thought that we thought that if even if that's not even if ground software is not part of the IV&V analysis, there's some value in looking at the utility functions or things that may be accessed by ground from an obvious flight software perspective. The second anomaly we have, the theme of it is our software hardware interface, and basically what happened is an antenna on a spacecraft is commanded to reorient by using certain increments of angle. So I'm going to try to, this is kind of, once you see it, it's an easier concept to understand, but for those of you online, basically, if you have an antenna, okay, let me find camera, okay. So we've got our antenna, and it needs to move this way. The way it moves is it kind of moves a certain amount of degrees, and then it moves a couple more degrees, and then it moves a couple more degrees. So it moves in increments. And basically, what happened in this case is that there was a fault protection limit for how far it was allowed to move in one specific increment, and that limit was tripped, and it didn't allow the antenna to rotate the way it was supposed to. It was suspended in mid-maneuver, which caused some issues. Basically, the way that this worked is that this particular antenna was able to move in 14-degree increments, and the flight software was capable actually of moving it not just in 14-degree increments, but in other degree increments as well. But there was a fault protection limit that said if we go over a certain amount of degrees in a single rotation, you start adding instability to the spacecraft, because we're in zero gravity, we're moving a giant antenna too far, and so it's going to rotate the spacecraft slightly, and we don't want to do that. So there's a fault protection limit set. And the way this kind of worked is, this is kind of a gross simplification of it, but there was a flight software counter that kept track of the movements of the antenna. So it would move 14 degrees, and it would trip a sensor that would say, okay, I moved 14 degrees, count up 1. And if it moved the other direction 14 degrees, it would count the other direction for a -1. And based off the value of the counter, they would determine when it's moved or when it's not moved, that kind of a thing. In this particular case, the issue was that we can move forward. Okay. The particular issue in this case is that either when we're back, either at the end of a 14-degree rotation, it would kind of move and then wiggle a little bit, or even at the beginning of a rotation, it would kind of like move back first and then go forward. So if, for the people in the room that can see it, basically it would either move and wiggle kind of at the end, or to start it out, it would kind of move backward a little bit before it went forward and then rotate. And in that particular circumstance, it would count backwards or forwards as a full movement in a trip on the sensor, which was interpreted as a 14-degree movement. So basically, what you had is you're moving in 14-degree increments for this antenna. Because of the wiggle, you get a net 0, because it says, okay, I move backward and then forward. So I didn't actually move 14 degrees. Flight software thinks that, but in reality, it did move 14 degrees. So what happened in this case is that it was counting the rotation. It said 14 degrees, 14 degrees, 0 degrees. and it knew that, wait, I need to compensate for that. So what I want to do is I want to command the next rotation not to be 14 degrees, but to be 28 degrees to compensate for the fact that for some reason I didn't move the last time. And that particular command tripped the rotational limit imposed on fault protection and said, no, you can't do that. It's going to rotate the spacecraft. And so it failed mid-maneuver. The project solution for this was to actually just remove the limit of the 14-degree rotation from fault protection to say that you can do that now. That's apparently what happened. So our observations is obviously removing that inhibit doesn't necessarily address the root cause of the anomaly. And roughly what this comes down to, I mean, again, this is a gross simplification, but switch bounce. If you've ever done any electrical engineering and if hooked an LED to a mechanical switch or something like that and flipped it, what you'll see without any compensation is the light is going to flicker if the LED is connected, because the mechanical part of the switch vibrates very slightly, bounces back and forth at the end. So again, gross simplification, but that's kind of what it comes down to, is that kind of an activity. So from IV&V lessons that we can see from this is that, I mean, I think primarily it comes down that even though we focus a lot on software V&V activities, that these don't occur in a vacuum. That there is hardware involved and that backs a lot of the software values that we see. So in these particular circumstances, the characteristics of these kind of mechanical rotations that we see, there's a lot of spacecraft that do have mechanical rotations and they use counters to drive those values. And that's interpreted by attitude and control and guidance and navigation to determine, determine at what state certain pieces are in the instrument. And we feel that we've seen a couple different instances of, in particular, what I would call unique mission scenarios tripping fault protection limits based off rotation and things like that. So not maybe nominal operations, but let's say a calibration operation or deployment, initial deployment mechanically of a certain component has tripped these kind of things across different missions where, and that's definitely not ideal. And so one of the things that we just wanted to take away from an IV&V perspective is that there are hardware components that drive some of the flight software values that we see. And taking things like that into consideration, understanding how the mechanics of the hardware work, where you could get a potential circumstance that if we are using counters to determine position or rotation of a certain instrument, that we might not get a value that we expect, or we might not get exactly what we predict. And so one of the things that we think is that should be something that drives our analysis as IV&V from a scenario perspective, is to consider those kinds of things, particularly counters for movable hardware. So, the second one, or this actually third one, is data storage and fragmentation. This is one that we've talked about before to a larger audience. One of the key things that I kind of wanted to take away from this is as far as the theme is concerned, this actual description is definitely geared more toward the fragmentation recommendations. But the longer we've been doing this, there's definitely some things to be said for data storage as well. So I may add some of those at the end just to talk about certain scenarios that we've seen that pretty much happen all the time. Basically what happened in this particular case is that data write operations on a spacecraft recorder failed. Because of that failure, the thing that was trying to write to the spacecraft was unable to do so. Buffers filled up, and certain traffic that was supposed to get where it needed to go was not able to get there, and some resets occurred. Kind of the background information on this. What's probably the best way to do this? for a fragmentation perspective, to understand the type of fragmentation that we're talking about in this case, imagine a drive that we have 10 gigabytes to use in the drive. The idea is that in this particular case, let's say a file that we need to write is required to write to 50 megabytes contiguously. So we have to have, in order to fulfill this write request, we need to have 50 megabytes in a row that we can write to put in a science file. And we have 10 gigabytes total. What basically happened in this case is that there's a circumstance where there may be more than 50 megabytes available on the drive, but there may not be 50 contiguous megabytes available on the drive. So because of reading and writing operations and all the things that happen on the spacecraft, this was a circumstance where there was, in fact, enough cumulative space to fulfill a write request, but there wasn't enough practical space to write the actual file that needed to be written. In fact, there was 87% capacity when this occurred, and so 13% remaining. And the data file that we were writing was smaller than the free space allocated on the solid state recorder. And the way that this worked is that there was a comparison made whenever a file write was to occur to say, okay, I need to write my 50 megabytes. Is there enough space to do it? The answer is yes, there's enough cumulative space to do it. So that request moves to the next level, which is getting to the file system to scan for a place to put this 50 megabyte file. Well, the way the file system was set up on the spacecraft is kind of typical for a lot of the file systems that we use in NASA spacecraft, is that basically the file system gets scanned to see where the next, from beginning to end, and looks for a spot, the next spot that can fulfill this request, and then just puts the data in that spot. In this particular case, obviously there was no space for it, so the whole file system was scanned. It got to the end, and it said, hey, we don't have any space for this, so let's discard this packet. Well, the next packet immediately comes along. It's the exact same size, exact same situation. The whole file system gets scanned again to determine the location for the packet, and I can't find it. So basically, that whole scanning of the file system started to take a really long time, and that kind of backed up the data to other parts of the spacecraft and caused issues. Project solution was, there was actually a posted flight rule not to let the solid state recorder get more than 90% full, which shows that they were aware of the condition, but also this occurred with 87% capacity full, so even its own flight rule probably wouldn't have done that. So data fragmentation, it's familiar, I feel, to most people that are used to data storage operations. Things that cause it extra are lots of read and write operations, things which may not. Also, when it's much more effect when the recorder is typically full. And basically, this is one of these data storage recommendations that we've seen is, regardless of fragmentation, across almost every project we've looked at anomalies that have had significant anomaly databases, there's going to be a point at which your recorder overflows. It doesn't matter if it says, hey, we have 3 days that we can run and we download all the time. There's going to be a point, because of some weird circumstance, because of ground, because of something that happens with spacecraft communication-wise, where your data recorder is going to get to its limit. And at that particular time, that's a scenario that we need to look at from an IV&V perspective. In this case, the fragmentation was the cause of that. But the project solution was to use flight rules, which are kind of tough to do because it requires constant monitoring in case if there are certain circumstances where you can't communicate with the spacecraft, it's hard to enforce that. From an IV&V lessons perspective, the first one is inevitability of data fragmentation, which isn't 100% accurate. there are ways to implement your data storage strategy that totally alleviate fragmentation, but typically that results in statically written data cells across the whole drive where everything has to write X amount of data. And so you do get some wasted space. So you trade what's in effect external fragmentation for internal fragmentation, which is slightly less of a problem, but you waste more recorder space. One of the things that could be advisable is that from IV&V lessons is enforcing this kind of memory usage through software under realistic operation conditions is something that is good to see from a test perspective, and also from a design perspective. This is one of those things where Monte Carlo analysis and could provide some certainty that within so many operations, there's a certainty that we're not going to overflow the reporter if we set a hard limit with 85% capacity. Data storage aspect is definitely, again, something that is near and dear to our hearts at the on-orbit anomaly research team, in that file system slowdowns, where not being able to write to the data storage device, those have been drivers for multiple anomalies across multiple projects, and is something from a scenario perspective that we feel that IV&V definitely needs to consider. Understanding how data is stored on your device from different sources, and what happens if data can't be stored anymore, what gets overwritten, is there a good strategy in place for these kind of operations? All right, we're getting a little close to the end here. So the next topic that we want to talk about is our communication protocols. And as a theme, communication protocols in general are difficult, especially protocol edges, which are the beginning and end of protocols. But in this particular anomaly that we're going to talk about, it was an edge condition. So downlink of the spacecraft's housekeeping and science data resulted in a generation of error messages backed by software and several circumstances. And so what happened here is this particular spacecraft used CCSDS, file delivery protocol, also known as CFDP, which is a handshake-oriented protocol. And to kind of understand what that is, again, without the whole non-graphics is killing me a little bit. But basically, a handshaking protocol is when one thing says, hey, I need this data. The other one says, okay, here's the data. Source one says, I missed part of the data. Could you please resend the pieces that I missed? And there's a lot of acknowledgments back and forth on where the data is sent. And eventually at the end, once the data is correctly sent and all the data is done, the transaction ends. So with CFDP, we're not going to go through the whole protocol in and of itself, but basically at the beginning is the request from ground to get a specific file from the spacecraft. So ground says, I need file A from the spacecraft. And the spacecraft says, okay, here's file A. At that point, the ground can say, I got all of file A, or I kind of missed pieces of file A. You need to resend some pieces of file A. So that's kind of the beginning. And we're going to skip to the end of the protocol, which at the end of the protocol, the spacecraft has downlinked all of its files to the ground. And so the ground has all the data it needs. So it knows that it has all the data it needs from the spacecraft. And so it sends a message to the spacecraft that says, I have all the data I need. The spacecraft gets the message, knows the ground has all the data that it needs at that point. So at that particular instance, the ground has all the data and the spacecraft knows the ground has all the data. So in effect, the transaction is more or less complete. But there's a final message sent from the spacecraft to the ground that says, okay, close up shop on this transaction, we're good to go. In this particular case, that final part was the issue. So what had happened is there was logic in the spacecraft that said, pretty much once I receive a message from ground that says, I've gotten everything on the ground, I know that I don't have to keep this data anymore. Because remember, data, it's a premium on a spacecraft. So I can get rid of it. And so even though I keep the transaction open to the ground to finish it all up, I don't need the data anymore. So it marks the data for deletion because it doesn't need it. And then it tries to reply to ground to finish up the transaction. In this case, the CCSDS protocol specification, which has been around for quite a while, says at the very end, if that last acknowledgement, which ground already has the data, the spacecraft knows that ground already has the data, but if that final acknowledgement from the spacecraft to the ground that says, okay, close the transaction, if that fails 4 times, the protocol says that we start back over from the beginning, where the ground says, okay, I need file A from the spacecraft. And in this particular circumstances, for unknown reasons, that final check or acknowledgement failed 4 times. And so the spacecraft, via the protocol, re-requested the file. Ground re-requested the file from the spacecraft, and the spacecraft had already deleted it because it said ground already has it, we don't need it anymore. So there were issues where the spacecraft basically couldn't find the file that ground was talking about, said it didn't exist because it had already deleted the file. And that's just one sample of communication protocol issues that we've run across. Yeah, so that's pretty much it. The cause of this anomaly, just try to wrap up real quick, was the implementation of the protocol. And basically, there was a ground workaround that said we need to wait a shorter amount of time between this final restarting of the transaction to make sure the file's not deleted. So one of the things that we wanted to talk about specifically with this, and we'll just finish up with this one because it's basically done, is that at IV&V, a lot of times we see with communication protocols refer to XYZ standard, that's been out there forever. This is how we're going to do it. And from the things we've looked at, there's kind of a recognition that explicit, elaborate requirements defining how the standard is actually implemented on the spacecraft is probably a good idea. And if not, it's definitely a good idea for IV&V to verify how the implementation of that specific communication protocol occurred. In this particular case, CCSDS has been around for a while, but in this particular mission, it may not have made sense to use the vanilla protocol for this particular instance. There may have been some evidence that that protocol shouldn't have been used. And basically, that's one of the things that IV&V needs to look at is communication protocols and all communication protocols. This just happened as VCFDP. It's a very common thing. We see that a lot. It's in our interest to understand that protocol specifically. There's other protocols that are communication, bus protocols, other things like that we use that are defined on the standard. And validating and verifying the implementation of the protocols, regardless if it's been around a long time. But new implementations, even of old protocols, have tended to show issues. So with that, we're going to skip the floor because my time's up.
The breakout session, anybody here in the room can go to the breakout session just outside the door, and anybody online can log into the breakout session. It's the same as what you're on right now, only at the end you put IVV-workshop breakout. And I'm going to switch over to our other presenter who is a remote presenter, so just give me a couple minutes.
Have any questions? It follows you around.
Freaks me out. Also, like looking at myself in the webcam is like, have you ever heard like echo on
whenever you're ready to get started,